36, we're writing and solving proportions. Reminder, proportion is just comparing congruent or corresponding parts. Okay, so if it was big to small, we're going to go big to small on the other side. It's a fraction equal to a fraction. So first thing we're going to do is we're going to talk about similar figures. Okay, so if we have two triangles and one's bigger than the other, but they hold the same basic shape, then these two things can be congruent, but only if they have a common multiple for each side. So they have this triangle right here, DEF on the right, and then this triangle here, ABC on the left. So we have 2, 4, 5 for our measurements here. Now, if this is a similar figure, okay, this will be our sign for similar, it's just a squiggly, then I can say that triangle ABC, okay, notice that I named it ABC just because it's in alphabetical order. There's no specific reason why I named it. But when I name my second one, I have to do it in its corresponding parts. So if I go AB, like side AB, then that would be its smallest side. So here it would be the smallest side, D, E, and then the last letter, F. So these are the similar sides, hopefully. So we're going to find out, we're going to verify that they're similar by doing a proportion. So what you do is you take its corresponding side. So here we have AB was the big one, so we're going to do big over small. Make that little note, big over small. So I have big, which was 2, over small, which is 1. And that should equal, and it doesn't matter which other side you use, but BC, we'll use BC, so that's big over small, EF. Notice this is the middle length side, It's 2. So the way I can verify this, if I don't look just straight across and notice that they're multiples of 2, I can do the cross product. And if the cross product works out, then we're good to go. So I do the cross product to get 4. Cross product to get 4, and they're equal to each other. So it does work out, they are similar. So when I start looking at these, the corresponding sides here are 2 and 1, 4 and 2, 5 and 2.5. Okay? So if they're congruent, which the angles here would be the same. So in a similar figure, angles are the same. So in a similar figure, all of the angles are corresponding angles. I should add that in there, corresponding. Corresponding angles are congruent. Okay? So all that means, congruent, is that, notice I put A and D in the same relative position, in a corresponding position. So A and D, because look, they're both across from the middle length, then they should be congruent to one another. So I know angle A should be congruent. This is the symbol for congruent. It's just an equal sign with a squiggly over it. It looks like that similar sign there. Is congruent to angle D. And same thing goes for the rest of the letters. So B and E are in the same spots. Look, they're both across from the longest sides. So angle B is congruent to angle E, and angle F will be congruent to angle C, and that's the last one. It's from the smallest side, across from the smallest side. And that would be all of your angle congruencies. Now the rest of these I would name similar, so I would say segment AB is similar to DE. See? And I would do the same thing with all the sides. BC is similar to EF, FD is similar to CA. All those concepts are the same. Okay. So as I write a congruency statement, I'm going to use these similarities here. Okay, so if I finish them out, I can use these similarities to write a congruency statement. So once I get these written down, I just simply take them and put them into proportion. So notice I have AB, which is from the big one. So remember, I was doing big over small. It doesn't matter if you do small over big, but they have to be the same no matter what you do. So if I'm doing big over small, I'm going to say AB compares to DE. So here we go. AB compares to DE. And that'll be the same as, again, big, which is BC, compares to small EF. So BC and EF. Looking at my last one, I put FD. Notice this is a small, and this one's the big. So I need to make sure that the big ends up on top. So AC was the big, FD was the small. So all these would compare. So when I put their measurements in their place, so if I said AB was 2, okay, measurement in its place, DE was 1. When I set all these up, they should all be congruent to each other. Basically, you could simplify the larger ones into the smaller ones, 2 to 1. So the scale factor would be 2, or the ratio would be 2 to 1, or 2 to 1. And of course, the obvious one is 2 over 1. Okay, but any of those three ways of saying similarity will work, and that would be your scale factors, how much they're changing. Okay, looking at the next page on example 1, we're going to start doing these. These don't just apply to triangles, it applies to all figures that are similar. So we can verify their similarities by simply looking at their angle measures. If all of their angles are the same, then chances are it is similar. If their corresponding angles are the same, then it is similar. So example 1A, it says find the measure of angle Q, so I'm going to write that down, measure of angle Q, and the measure of angle W. So again, I look at my figure, and it tells us at the beginning, it says PQRS. So let's look at our figures. It says PQRS is similar to, keeping in mind the order, WX, Y, and Z. So if they're similar, this should make our life a lot easier because all of the angles should be congruent. So if I say P and W are in the same spots, which they were according to the similarity statement that said so, okay, so P and W are in the same spots. So I should look at that and go, okay, P is definitely the same as W, so W has to be 120 degrees. So we're going to equal 120, and do not forget your degree symbol right there, otherwise we will end up with missing points that are not necessary. Next, I'm looking at Q. Q is in the corresponding spot with X. We can see that in the picture, but if we didn't, I can look at Q and X and then the corresponding spots in our similarity statement. So again, I go Q and X are the same, that's 80 degrees. And these are really quick problems for that reason. Okay? If we identify their corresponding areas, then it makes our life really easy. Just a reminder, this box right here is a right angle, so it's 90 degrees. Okay. Another little fun fact, if it's a quadrilateral, meaning 4 sides, then it is always going to add up to 360 on the interior angle. So if I added them all up, like 120, 80 makes 200, 270 when you add in this bottom right corner, and then 270 plus 90 makes 360. So you can verify your measurements by adding them all together. Okay, so there's that one. Now it says find the scale factor from one to the other. If they are similar, which it tells you in the similarity statement right here, this was given to us, that it is similar, I can take that little bit of information and use it in my statement. So looking at the sides, these pictures are really nice. I can go big to small or small to big. Doesn't matter. I prefer to go big to small. It makes an easier proportion when I do it. Okay? And I highly suggest you do the same. So I go big, which would be, in this case, I'm going to do PS, will be 3. To small, the corresponding spot is 2. Okay? And then that should be equal to whatever I can reduce it to. So all I do is take my corresponding places, set them equal to each other, and see if I can reduce it at all. If I can, then I do, and if I can't, that's all I have. There's nothing I can do with it. So this one, in this case, I can't change that scale factor. So I'm just going to write that it is the scale factor. I'm using the abbreviation SF. Okay. So the scale factor is 3 to 2. So I could write that in 3 different ways, right? 3, 2, 2, or 3, 2, 2. Any of those three would be fine. Okay. Let's go to part C of that. And it says use the scale factor to find QR and ZY. So QR is labeled A, so that's going to be our big. So I'm going to go ahead and start it. It said it was 3 to 2, so I'm using my scale factor. 3 to 2 should be equal. Remember, big to small. So QR was a big, so that's A. We don't know what it is. To small, which is XY of 5. So in order to solve this, just do your cross product. 2 times a is 2a, which is 2 times a, right? 5 times 3 is 15. Finish solving it out. I have to do the division property of equality, divide by 2 on each side. That cancels out. So a is equal to 7.5. If they don't give you a length of measure, you write units, of course. Okay, so it is 7.5. And I can do that with all of the sides. So when it says to find zy, again, my scale factor is what I'm going to use. So my scale factor was 3 over 2 is equal to zy was b. Okay, so I know I'm going to have a factor. It's big to small. So b is the small, so I'm going to put it on bottom. And then that corresponding side is SR. So I'm going to take SR, which is equal to 6, put it on top, and go ahead and find my cross product. So I get 12, I get 3b, just drop down that equal sign, finish it out. Division property of equality allows me to do that. B equals 4 units, because they didn't give us a unit of measure. Alright, that was in. When I write down my answers, it asked me to find the length of the sides. So even though the letters were identified, we have to say that 7.5 was actually the measurement for segment QR. So QR is equal to 7.5, because that's what they wanted us to find, was the length of QR, not what A was. They wanted us to find what the length of QR was. Then over here it said find the length of ZY, so we have to identify the length of ZY as 4. And then these are our actual final answers right here, because it asked us to identify the length of each of these segments, so I need to write them down. Okay. Next question is going to be example 2. It says using indirect measurement. So this is probably the most interesting way to do this, because you can set up a proportion using, let's see if I can dim this down just a little bit. I can set up a proportion using myself as a guide and my shadow as the other part. So what's interesting about that is that I can find the height of any telephone pole, or I can find the height of a building, especially at high noon when our shadows are really small. So I'd measure off of my inside foot with my shadow, and then measure how tall my shadow is, and then obviously how tall I am. And I can use this proportion because the sun will always be at the same angle right here, because our angles will always be the same, and this will always be at 90 degrees, leaving this one having to be the same. Since all three of our angles are the same, then we will be similar. But what's interesting about it is I can find the height of the Sears Tower if I wanted to by simply measuring my shadow, and without actually having to stretch the measuring tape all the way to the top of the thing. Okay? All I need to know is a few basic pieces of information. So if I know my height, the height of my shadow, and the height of whatever I'm measuring's shadow, then I can do that. I just set up my proportions. I'm going to go big to small again, just for the consistency's sake. So I go big, which was, I'm going to do the one that we know first. So it's shadow over our small shadow, so 10 over 4. It's going to be equal to, again, I did big over small, so big here is x over what I don't, which is my height, 5.5. Now, if I was 5 foot, this is 5'6", right? I would have to convert this to just feet. I don't want a combination of things. So if someone puts their 5'8", I would have to convert that to just feet. So I'd take 8 divided by 12, and whatever that decimal is, I would put it down. Okay. So here we go. Start doing our cross product. We get 4x, and then here we get 55. So I got 55 equals 4x. I divide that by 4 on both sides using the property of equality for division, and then I should get my answer. Let's cross out. X equals 13.75. So I write down my answer as x is 13.75. Therefore, this radio tower that we were actually measuring on this one, the radio tower is 13.75 feet tall. And that's the end of my sentence. So here's the answer to my question. It asked how tall the radio tower was, and there we go. Okay, you can't just identify the variable. We have to label it and then put it to answer the question. Okay, going on to the next example. We're going to do what's called a scale drawing. So if I guess when you see these maps of houses, they don't always, or they shouldn't draw them to full scale, because if they did, they would be ridiculous sizes of paper, and you could literally be a floor plan. So you wouldn't draw, if I was trying to demonstrate the size of this room, I wouldn't draw something that is literally the size of this room. I'd probably measure it, and whatever my measurements were, I'd convert them down to a smaller unit. So I would say, let's say millimeters. If this room was 30 foot by 45 foot, I would change that to 30 millimeters by 45 millimeters. Therefore, every 1 millimeter is 1 foot. So this is my scale factor for this room. Okay, here's my attempted drawing of this room. I think I said 30 by 45. So the actual is 30 by 45 feet. But in my drawing, I'm going to convert them. I'm going to write a key that says 1 millimeter goes to 1 foot. So that's my scale. That's my scale right there. So in my drawing of this, this is my actual. In my drawing of this, I would make my note scale, and then 45 millimeters would be my measurement here, and 30 millimeters would be my literal distance to here. That way when somebody is doing this and maybe they're trying to recreate the room, like for instance in some kind of crime scene investigation, if we were drawing out the layout, we would need that to be able to do it. So we don't have to draw the actual size of the room. We would need a scale factor. That way when they recreate it, or if they're using it in court or something, they have actual factual data as to where something was, how far it was, and then when they analyze it, it becomes more accurate. So they would say that 45 to 45, 30 to 30, those are the corresponding spots. So let's do the example that they gave us. Example 3. So this is my scale drawing. Example 3 will be using an application of scale drawing. It says a desk is designed to have 3 drawers on the right side. So on the right side. In the scale design drawing, the width of the drawers is 4 centimeters. So make a little note, width is 4 centimeters. If the scale of the drawing is 1 centimeter, is in factual reality 7 centimeters, then how wide will the actual desk drawers be? So I take my scale factor, which is 1 to 7, and I would set it equal to, okay, remembering this is drawing to actual, So here it says in the drawing it was 4 centimeters. So this is drawing to actual, and we don't know what actual is. So I'm going to give it an X just for whatever reason. I could put in a W, I could put in any variable. You can put in the first letter of your name. I could put a B right there if I wanted to. Then I do my cross product. So I get 7 times 4 is 28. X times 1 is just X. And, well, there's my answer already. So to answer the question, X is 28 in this case, which was my missing variable. So now I need to answer the question. What is the actual width of the desk drawer? 28 centimeters. And that's it. Now I'm done. So I take my scale factor and I compare it. But always keep in mind that this is drawing to actual, or whatever it may be. And this would have worked out the same way if I would have did big to small. So if I would have done big to small, 7 to 1, and then I compared it, because this time it was actual to drawing, I would have taken my actual, put an unknown there because I didn't know what it was, to my drawing, which is 4, and when I multiply it, I still get the exact same thing. So it didn't matter which way you set it up, but it has to be consistent. If I put actual on top, it needs to be actual on top on the other side. Okay? And here is an interesting one. The ratios of perimeter, area, and volume always follow this way. So if it is perimeter, for perimeter it will look like whatever the measurement of the perimeter to the measurement of the perimeter would be. So either big to small or small to big, doesn't matter. But for area, it will need to be whatever the area is. It's the square part of it to the square part of it. And then we go on to volume, remembering that volume is cubed. It follows that same concept, a to the third and b to the third, because they again are cubed. Okay, so I have to compare them as volumes to volumes, areas to areas, and perimeters to perimeters. I can't go around that. Okay, so example 4a asks us, what is the ratio of the circumference of the two inner circles to the circumference of the outermost circle of a dartboard that is composed of concentric circles, just meaning inside of each other, right there, concentric circles, do that. And then it says that the inner smallest radius is 1, and with each consecutive circle the radius increases by a width of 1. So I'm looking for the ratio of the two innermost circles. So the two innermost circles are the one with 1, and then the one that will have a radius of 2. So we're recalling that circumference, because that's what we're looking for, right? It says, what is the ratio of the circumference of the two inner circles? The circumference measurement gives us a 2 pi r. I'm going to leave them in terms of pi, just for simplicity's sake, because when I do my ratio, it'll simplify out. So I need to find the circumference of the small. So I'm going to put C sub s for circumference of small. The smallest one is 1 for the radius, so I'm going to put 2 multiplied by pi multiplied by 1. And when I simplify that, I get 2 pi. And I'm done for that one. Now I'm going to do the circumference of the bigger of the two, and that one has a radius of, when I add the second 1 on there, it's 2, so it's 2 pi times 2, and I get 4 pi. Now recalling what they said, find the ratio of the circumference of the inner two circles to the circumference of the outermost circle. So I want to look at the outermost circle. So I found the circumference of the inner two circles. Okay, so I got the smallest and I got the inner two. Now I'm looking at the largest one of them all. So I'm going to do circumference of the largest, so the outermost circle. So I'm going to count these. It goes 1, 2, 3, 4, 5. So the radius is 5. So 2 multiplied by pi multiplied by 5 gives us a total circumference of 10 pi. Now, looking at what they asked us to find, we'll read the question one more time. What is the ratio of the circumference of the two innermost circles to the circumference of the outermost circle? So the circumference of the innermost circle was simple. It was the two innermost was this one, the bigger of the two that I did first, which is 4 pi. So to that of the outermost, and that one was 10 pi. Now I should notice that my pi's will cancel, which leave me with a 4/10, but that's still not simplified, because I still have to reduce this down to, if I divide each one by 2, 2/5. And I'm actually done there. Now the second part of this question asks a simpler question. So keep in mind, ready, I've already got the one that compares the perimeter. Remember, circumference is just perimeter of a circle. So this would be kind of like my perimeter, okay, was 2 to 5. So in theory, if my perimeter was 2 to 5, then my area should be 4 to 25. So what we're going to do is we're going to try to verify that. We're going to verify that by finding the area of the same thing. So I'm going to find the area of this circle and the area of this circle and go from there. So I'm going area of the B one that we set up before, remembering that our radius was 2. And for area, we use the formula pi r squared. So I'm going to take my radius, which was 2, and I'm going to square it. So 2 squared multiplied by pi. And I get 4 pi. Then I'm going to find the area of the largest, which was this one right here, and my radius was 5 here, so it's 5 squared pi, which leaves us with 25 pi as my answer. Now, so I can compare this to that. So I have 4 pi compared to the largest, which is 25 pi. And my pi's cancel out, so I'm left with just 4 over 25. Now, it held true. Notice my perimeter was just my two numbers over each other. Now, my area was squared, which was 4, and squared, which is 25. So it worked out. And if I was to predict what my volume ratio would be, I would simply take my perimeter ratio, which was 2 to 5, and I would cube it. Therefore, my answer would end up being 8 to 125 if I wanted to find the volume comparison. Okay? So it's a nice, easy way to jump from one to the other very quickly. Okay? That's all you need.